Welcome back to this video that has the aim to put all together what we have learned so far in programming in ROS. If you remember from the last video, we have seen how to draw a pathway of an S shape with Turtlesim. We have done that by writing a Roomba controller C++ file, which is a node that subscribes to the topic pose and publishes a message of type geometry message twist on the topic command val. If you don't remember that, feel free to check it out on the link popping up now. Let's run it so we can refresh what this node is doing. And as always, run the ROS master. Then you need to run the Turtlesim node. And finally, run the Roomba control executable file. You can see that the turtle is drawing a S shape. The turtle is subscribing to the turtle1 pose topic, and this allows us to detect a pose that is greater than 10 in X and return left, as well as it turning right when the pose is less than 1. Furthermore, when the position in Y is greater than 10, we start over from the position x1, y1, and we clear the pathway drawing. We have done it by raising a request to the service teleport absolute and the service clear. Okay, after this refresh, we are ready for handing over. The goal of this project is to make the turtle go to a goal position. We are going to do that by creating a service that, as request, gives the goal position and orientation, and in response the service will give back the angle to turn and the linear velocity necessary to reach the goal position that has been requested. In the last video we have created the service structure and messages, and now we are going to code the server and update the Roomba controller nodes. So let's start by creating a service server that calculates the angle that the turtle needs to have to go from the actual position to the requested position. And let's create a new C++ file and call it go-to-position-server. Let's include the needed libraries and above all the service header file that we have created in the last video when we have created a custom service. And if you don't remember that, feel free to check out the video in the link popping up now. And include the pose and the position to the header file. Let's create the main section first, and this is gonna be a simple one because we are handle the whole service as a class. And first initialize the node, call the class, and use the spin function and return 0. That's all for the main function. As you can see, it's very simple one. And now we are going to make our hand dirty by coding the position server class and create the constructor section and the private section. We are going to use a similar structure as we already did. And first of all, let's go in the private section and create the node handle object, the subscriber needed for subscribing to the turtle pose topic. Create a service server object, pose to the object, and we're gonna call it current_pose. Do the same thing for the pose object, and finally we need to create a target position object that will be our service. Now we can build our constructor, and for doing that we can create the subscriber that is subscribing to the Turtle1 pose topic that is going to handle the data thanks to the callback function that we are about to code. Same things for the server that will be called thanks to the service goToPosition that will be of type target position. The service will be handled by the server_callback function, which will make all the needed calculations. Let's create the callback of the subscriber function, and we're going to modify our pose to the object. This is a very simple one, and now we create the server callback function that will receive a service request and response, and we're gonna call it rec and res respectively. Okay, now we have everything we need to calculate the steering angle that the turtle needs to take to reach the goal position. The formula is the arctangent of the difference in y and x of the current and the target position of the turtle. This can be retrieved easily with some basic trigonometry. Then we are associating that angle to the response.angular_z. Then we can print on the terminal some information like the angle that has been calculated so far, and then we can fill out our response message, and for the structure of the message it will be linear_x equal to -1, and you will see later on why that and why we're gonna put that value. Then we're gonna put our feedback message that from the service definition, I remember you that is of type boolean value, and finally we're gonna make a message which is of type string. Then return true, and that's all for the service. What we can do now is to try it, but first I remember you that we need to update our CMake list file, asking CMake to create the executable file from the file that we have just coded. So build the package and see what happens. Okay, it seems that I made a mistake, so let's correct it right away. And now it's done. We have our server correctly built. Start the Turtlesim node, the Roomba controller, and turn on the server. As you can see, it is working, but doesn't make anything. Why is that? Well, because we don't have a client that is asking the service to do what the server is doing in this moment. So we need to have a client for doing that. And we can create one client in our Roomba controller node that will call the service go-to-position. Let's include the target position header file and the IO stream to print some message on the terminal. Now we can initialize our client object that will raise a request to the go-to-position service that is of type target position. We can call it client underscore target underscore pose. So it's gonna be client target pose. Finally, we can initialize the service object, and I remember again that it will be of type Roomba message target position, the service that we have created from scratch in the last video. So now we have everything we need to create a service client that is asking a request to the service of type target position, and the name of the service is go-to-position. And remember that it has to be, of course, the same as the service server. Now we can set the request of the service giving, for example, a target position in X and Y and the orientation in theta. And we can put 3, 3, 0, but this is just an example. After completing this tutorial, feel free to change this value to see the behavior of the turtle, and you will see that it doesn't change nothing. Now we need to write what the turtle needs to do if the client raises the request. And I remember that the client returns a boolean value, so if this calling is true, then we do something. And so, if the client object calls the service object for which we have set up the request, we can start to print some message on the terminal. For example, the message that belongs to the response of the service itself. The service has been called, and the service itself has in memory the value of theta calculation for reaching the target position. So we need to stop the robot and rotate on the same position till we reach the target position dot response dot target theta. For doing that, we can see that if the difference of the current theta and the target theta is greater than a threshold that we are about to set, spin at the angular speed of 1 counterclockwise. And now the calculation is done. So let's set the threshold, and we can put at 0.05 as an example, and calculate the difference value, which will be the difference between the current theta angle and the angle theta that the server has calculated, and gives as output in the response dot angular underscore z message. Now let's build the package and check it everything if is okay. In fact, I made a mistake and let's correct it right away. Build the packaging again and we can see that the packaging is built correctly. So now we can test it. As you can see, when the service is called, the turtle starts to spin with the linear velocity in x0. We are always in the condition inside this if statement. If we kill the server, then the turtle continues from the position that has at the moment. And if we call the server again in another position, the target position dot response dot angular z angle is different, and the turtle is always spinning. Of course, there will be a certain point where the difference is less than the threshold that we have set. But since we don't code the condition for that, the turtle keeps spinning. So what we can do now is to code the condition for which the turtle approaches the target position dot response dot angular z angle. So else if the difference is less than the threshold, then we stop spinning and we put the linear velocity to -1, which is the target underscore position dot response dot linear underscore x message value. And if you remember, this value has been set up on the server when we code it. So let's build the package and test. And you can see now that when the service is called, the turtle is spinning till he reaches the target position response angular z angle. Which is the angle that the turtle needs to have for going to the goal position that we have set 3 and 3 in x and y. Now you can see that something smart happens. At a certain point, the turtle starts to spin in one point, instead of continuing his pathway in linear velocity in x. So what's happening? Well, we have reached the target position in x and y, and if we overpass this point, the target position response angular z angle is changing, so we fall in the condition where the difference value is greater than the threshold and is not be less than the threshold anymore. This means that we have already reached the target position at least in x and y. And now let's try it by raising the service in another position of the pathway, and we should see the turtle stop at the same point. And yes, as you can see, it stopped at the same point, that is gonna be x3 and y3. So feel free to try several times at this point for checking that everything works fine. Okay, now we are very close to the goal of this project. The turtle for the moment is reaching the goal position when the service is called. But what we need to do is to stop the turtle when the turtle reaches the target orientation angle that has been set as request as 0. So this condition can be achieved when the difference between the current theta and the target position request theta is less than a threshold. Both linear velocity in x and angular velocity in z should be 0. So if the difference between the current theta and the target position dot request theta, that we are calling it diff underscore theta, is less than a threshold, and the distance is less than the threshold as well, set the linear velocity in x and angular velocity in z to 0. And print the message that the target position is reached. And why not, we can call the clear underscore pathway service to clear the pathway. Now we need to create a new value called diff underscore theta, which remember you is the difference between the current theta angle and the target angle. And we also need to calculate the distance between the current position and the target position in x and y. And if you want to do that, we are going to create a function called getDistance, which is basically the distance calculation between two points in two-dimensional environments. Basically, the node should be done, and let's test it right away. So run the node, and as you can see, the turtle reaches the position in x and y, and when it reaches the target angle, now it is stopped and the pathway is cleared up. Then you can kill the server and make the turtle continue to do his S shape from the target position. Let's call it from another position to check. And as you can see, it seems that the code is reliable regardless the position of when we are calling the service. So congratulations, you have learned how to make the turtle go in a target position using custom service. I hope that you enjoyed this tutorial and that you get a lot added value out from this. I wanted to point out that this is only one way to do it, and you can try it with the Python code provided by the wiki.ROS. I can provide the link in the description down below. So feel free to write down your thoughts about this tutorial, and don't forget to subscribe to the channel for learning much more in ROS, and if you want to benefit from one-to-one discussion on your robot application, regardless the complexity. And thank you for staying with me till the end of this video, and keep learning robotics with ROS.